So first of all, thanks everybody, and I'm glad to see that a larger community is building here. So thanks, Oscar and Robert, for actually organizing it. And I'm happy to share actually that I attended ADBIS 2007 to 2009, so it was Varna, Pori, and Riga, and I'm glad to be back. So I started as a young PhD student, and now I'm a professor, and happy to come back actually. All right, so this talk is all about system infrastructure for data-centric ML pipelines. So first we need to define what is a data-centric ML pipeline. So first there is some kind of training procedure where we have a feature matrix X and labels Y for classifications. Those are categories. For regression, this is a numerical response variable. So we have this iterative training procedure that creates us a model, and then we can utilize this model to do inference or scoring, getting new data and essentially applying this in practice. And then you might get an accuracy of 85%. Most of you might utilize existing libraries, so we usually wrap this into training and scoring or prediction procedures. However, data-centric ML pipelines are much larger. So similar to normal ML pipelines, you have some form of data preparation steps up front. So you get potentially categorical features, and you have to perform some kind of feature transformation. So dictionary-based coding, one-hot encoding, you might perform binning to expose non-linearities even for linear models. Furthermore, it's good practice to actually go through outer loops for hyperparameter tuning and cross-validation, as well as model and feature selection, so the general term of AutoML, that we try to automatically find the best performing model. Now, in data-centric ML pipelines, we essentially have additional outer loops around that for data programming and augmentation. So starting with a small label training example, performing synthetic transformations or transformations in order to generate synthetic training examples, which is known to often improve accuracy. And additional outer loops are there for often data cleaning and preparation, where we try to enumerate effective data cleaning pipelines that ultimately yield better kind of model accuracy. And on the other side of the spectrum, we have additional data science tasks for data and model validation, as well as explainability and debugging. So in our group, and this entire spectrum essentially spans what we call a data-centric ML pipeline. And the main premise there is that creating a high-quality data set is often way more important than small algorithmic differences in the models that we are training. So in this entire scope, we've done quite some work. So here you see a reference for SliceLine for model debugging. I will talk some more about this. Then recently we had work on how to perform efficient parallel feature transformations, as well as how we enumerate actually data cleaning pipelines. However, data-centric pipelines are even larger. Some of you might come from a core data management perspective, something that we nowadays call data engineering in the context of ML pipelines. So how do we get actually heterogeneous structured data into a form that we can train machine learning models over? So aspects that are really relevant are first, data extraction. So we recently had some work how we can take custom data formats and by example of getting hundreds of examples and then automatically generating efficient extractors and readers from those heterogeneous, very custom data formats, as well as alignment of multimodal data. So many of you might work in actual applications and use cases. So we've done quite some work in automotive, healthcare, recycling, and there you have multiple modalities. So in a car, you get multiple video streams, front, rear, left, right. You get a mobile eye camera. You get irregular time series from the entire CAN bus system, which is about 1,400 time series for every button and every sensor in your car. And unfortunately, all those modalities, they are not aligned. So you can't just create a matrix and feed this into an ML model. But for example, if you drive into a tunnel, many cameras have dynamic frame rates. So if your video stream is compressible, the frame rate is lower. And ultimately, we need to perform a spatial temporal join to bring the same events into a single single rows in a matrix. So those are essentially major challenges in this larger context of data-centric ML pipelines. Now, a key observation is that many of those primitives are actually hierarchically composed out of library functions and additional custom code, and most of the state-of-the-art algorithms are themselves based on machine learning. So state-of-the-art data cleaning is in fact utilizing machine learning. So given that observation, it makes absolutely sense to build those kinds of primitives on top of machine learning system infrastructure, and that's exactly what we're going to do. Before I tell you a little bit more about the internals of those system infrastructures, I would like to make a general case for optimizing tensor computations. So this is a slide that Matteo Insolandi and Chris Germain, together we gave a Sigma 23 tutorial in Seattle this year, where we make a general case for tensor computations as a narrow waist for a lot of different computations. So Matteo, his team is working on how to map query processing onto tensor operations to better utilize hardware accelerators. My group is working on the end-to-end data science lifecycle, and Chris Germain for decades works on simulation and sampling. And as it turns out, we can map all those broad areas actually to a narrow set of linear algebra operations such as matrix multiplications, aggregations, statistical functions. So it can really be this narrow waist, which then allows us to efficiently reuse compiler and runtime infrastructure to utilize emerging modern hardware. So you're probably all familiar of the end of Moore's law, the end of Dennard scaling, where we face fundamental hardware challenges, and how the industry is addressing those hardware challenges is by increasing specialization. So you can expect in the next decade more and more very specialized hardware accelerators. And usually the first thing hardware vendors are providing are efficient libraries for linear algebra. So by essentially mapping a number of different applications to tensor operations that utilize matrix multiplications, and the hardware vendors providing highly tuned libraries for their particular devices allows us to quickly reuse and gain out-of-the-box high performance and scalability. So I want to talk a little bit more about data science, and that it's actually true what I just said, that we can cleanly map a lot of those applications to linear algebra operations. So the first kind of example I want to give is a work we've been doing for at least 3 years now on efficiently enumerating effective data cleaning pipelines. So Shafak, which was my second PhD student, did a great job of building an entire library of robust parameterized data cleaning primitives implemented in linear algebra. And then we are utilizing evolutionary algorithms to find the structure of data cleaning pipelines. So should we first apply outlier detection followed by missing value imputation and other strategies, as well as hyperparameter tuning for the hyperparameters of those data cleaning primitives. So to give an example, here you see kind of an input with 2 features that's dirty data that has essentially corrupted data, where some of the universities, so TU Graz is located in Austria, but some of the entries incorrectly essentially point to Germany as the country. Now, once a primitive is, for example, the cleaning by robust functional dependencies, where we in the first step try to identify functional dependencies. Whenever we see TU Graz, this should map to Austria, but in a robust manner where we attach a threshold saying if 90% of the value pairs agree, then we assume this as a functional dependency and can then utilize this functional dependency, obtaining the majority value to clean up the remaining values. And of course, this threshold is highly data dependent, so we need to tune that. Other strategies are mice. So this is multivariate imputation by chained equations. What it does is very simple. We extract individual columns that have missing values. We rearrange rows that we take the existing values. So this now becomes our label. We take all the other aligned tuples. We take existing values and train a model on top of that. So if it's a feature with categorical values, this becomes a classification problem. If it's a feature with numerical values, it's a regression problem. And so we repeatedly extract essentially the columns with missing values. Existing values is our training set. The missing values, that's where we then apply this model to impute new values. Yeah. And how the entire infrastructure then goes is that we have some input data, we have a target ML application, and that fundamentally differentiates it from existing data cleaning, where you get only the data set and clean it, and you have to make a lot of assumptions. Here you have the machine learning application. You can train models on the validation data set and test it there, or on the training data set and test it on the validation data set, in order to get the signal how good was your configuration of a data cleaning pipeline. So you can partially automate this process. I want to admit, fully automating this process is completely unrealistic. It's always a semi-manual process. And what we try to automate are the mechanical aspects, where data scientists tries repeatedly via trial and error certain configurations, evaluates it, and then comes back. So what we are doing, we first enumerate logical pipelines that are representing the structure of data cleaning primitives, which primitive after which, with evaluated with default parameters. And then for the, and we are doing an evolutionary algorithm where we essentially evaluate a population. We take the upper half, the best half, we create transformations on them. We add a primitive, we swap primitives, we remove a primitive. And over multiple populations, essentially come then to a good set of logical pipelines. And then we are using hyperparameter tuning in order to actually tune the totality of all their hyperparameters. And finally, we return the top K data cleaning pipelines, again, in the premise that the user needs to be in the loop. So the user gets then a set of top K primitives and says, oh, this one is totally overfitting. I take the simpler one and I might be able to modify it by hand and then continue actually utilizing this pipeline. And because of all the data cleaning primitives are implemented in linear algebra, our optimizing compiler that I will later introduce can automatically generate distributed data and task parallel programs. So task parallel, if the data set is small, we're just running lots of those pipelines concurrently on a cluster. If your data set is really large and doesn't fit in memory, we are actually running the individual pipelines in a data parallel manner and parallelizing over individual partitions. So that was on the data pre-processing. On the model debugging, I can make a similar case. So this is the slice line paper. Svetlana was my first master's student actually at TU Graz. And what we are doing here is we want to find the top K worst slices, where a model performs significantly worse than on average. So imagine we trained a model, on average it gives you 85% accuracy. Now we want to find slices in terms of conjunctions of attributes such as gender female, degree PhD, where the model potentially performs much worse, like giving you 55% accuracy, which is an indicator that this slice might be underrepresented. You should go ahead and find more training data for it, or otherwise via rules and neurosymbolic kind of formulations improve those particular slices, so groups of data. Yeah, there was prior work on that, but what we've done, we essentially devised a very intuitive scoring function that balances the slice error and the slice size, which with a weighting parameter is nicely balanced. So a slice that is twice the size than another slice and has half the error has exactly the same weight. And then the key idea, what we are doing, we actually perform an exact lattice enumeration. You might say the lattice is exponentially large. How can that be feasible? The key is really pruning. And the pruning is inspired by traditional frequent item set mining. So the a priori property of saying a slice can only be frequent if all the parent slices are frequent as well, because we're talking about conjunctions of attributes. So if the slice degree PhD is not frequent, the more restrictive degree PhD and gender female cannot be frequent if the parent is not frequent. And that allows us to prune effectively nodes in this lattice and all reachable children from there. And what you have to realize is, as we descend down this lattice, the number of parents increases. So in the first level it's 1, second level 2, third level 3. And because we are taking the minimum, if at least one parent is not frequent, we can rule out this entire node. The pruning power actually increases, which allows us to effectively enumerate the entire lattice. And then we formulated this entire formulation in linear algebra. So enumerating a single lattice with pruning is a single Boolean matrix multiply, or integer matrix multiply. So the inputs are Boolean and the output are representing counts, how many predicates are actually matching, and then we are just comparing against the lattice level, and can, with support for sparse linear algebra, effectively actually perform those operations. So that was model debugging. Let me give you a couple of additional examples. You're probably familiar with data augmentation, so taking a small labeled training data set and generating synthetic labeled examples. So even the famous AlexNet paper that essentially created this deep learning revolution in 2012 again, that won the ImageNet challenge in 2012, had an entire section on data augmentation saying that it improved accuracy by 3 to 4%. And they did simple things such as take image patches of 87%, compute reflections, because we anyway want to train a model that is invariant to the orientation of objects. And essentially it did noise modulation, stretching, shearing, and in general, you want to apply transformations that create a better coverage over the actual domain in practice. So data augmentation, one aspect. The second is graph processing. So Katja talked about knowledge graphs. There's a number of machine learning algorithms on top of graphs, such as connected components, PageRank, shortest path. And one way of computing the connected components is simply maximum propagation. So every node gets its vertex ID. We propagate in every epoch the maximum observed in the node to all its neighbors. We aggregate that via a max and propagate it further, right? And so through multiple steps, essentially the maximum vertex ID in a connected component propagates through this component but can't reach other subcomponents, and then we simply collect the distinct vertex IDs. Now in linear algebra, it's as simple as this code. So this is literally taken from our primitives, from our domain-specific language with R-like syntax, where the main computation is literally just a sparse matrix, a graph G, element-wise multiplied with broadcasting with a vector, which are the currently observed maximas, propagated through all the different columns, and then a row max, which is this aggregate all the messages that we received in a particular node. And then you can actually run this really at peak memory bandwidth of how fast you can scan this graph, and then you iterate a few times and you're done, right? So very nice formulation. And of course, there's a number of additional machine learning algorithms that can be cleanly mapped into linear algebra as well. And recently, so yesterday we had the D&I panel, there's lots of work on how we can enforce certain constraints, such as group constraints, where for certain groups of people, you ensure that the false positive, false negative rate is the same, and how you actually include that into a training procedure. So there are formulations where you simply modify the loss function and convert a constraint optimization problem, so optimize the loss subject to those fairness constraints, into an unconstrained optimization problem that you can nicely optimize. So the key takeaway here for this first part is, for all those different applications along the entire data science lifecycle, there are really clean mappings, if you think a little bit about it, into linear algebra operations, which allows us to subsequently focus on optimizing those tensor computations. Yeah. So I hope I could make a case that optimizing tensor computations is important. Now I want, in the second part, to talk about the system infrastructure we are building for the last decade for those kinds of data-centric ML pipelines. Before I start, I want to utilize one key concept you should all be familiar about, which is data independence. So I want to make a case that it's of utmost importance when building such a system infrastructure that we try to separate concerns and provide data independence in multiple different dimensions. So the first one is the data representation. So there are various algorithms that can utilize dense, sparse, compressed representations, and it's nowadays actually a mega trend in machine learning, all the way from algorithms down to the hardware to efficiently support sparsity. So not just dense matrices, but some form of sparsity patterns. Second, data placement. So we will talk about local versus distributed operations, but I also alluded to those different, more specialized hardware accelerator devices, and this will continue to grow in the next decade. So we will see lots of different devices, and we need to be able to map to those different devices. Furthermore, in the last couple of years, there was also a specialization in terms of data types. So in order to get better instruction parallelism, you see lots of different new data types, such as doing inference in int8 is very common. For training, utilizing bfloat16, or the new data type by NVIDIA, the TF32, which is supposed to be a drop-in replacement for 32-bit floating points, but they only have 18 bits because they sacrifice a little bit of precision while preserving the range to still be able to accumulate certain values. Yeah. Furthermore, we see an increasing diversity of data modalities that we have to support and efficiently embed into this representation. Now, data independence is an old topic, so I hope you all remember Ted Cott's famous paper on the relational model and calculus. And then later you had those great annotated versions, and one by Joe Hellerstein brought up this famous Hellerstein equation of saying whenever the environment changes much faster than your application, it's worthwhile to invest into a declarative description languages and system infrastructure that automatically compiles plans. So in our case, the application are existing machine learning algorithms, and the environment also is changing data types, changing hardware accelerators. And with that, actually, there's a fundamental need for data independence. In the next couple of slides, I'll show you a couple of our research projects that go into the direction of data independence as well. So the main umbrella project of my group is Apache SystemDS. So what it does is it takes a domain script in a domain-specific language with all-like syntax, such that the burden of learning a new language is not as high, and then goes through an optimizing compiler and generates hybrid runtime plans of local in-memory operations and distributed operations and MapReduce and Spark. So it started in 2010, really with MapReduce. Nowadays, we deleted this backend and we primarily use for distributed operations Apache Spark. And then as deep learning became really important, so in 2014, we started adding our GPU backends. And in the last, before I go there, so initially it was a proprietary IBM product, and then we decided to actually make it open source, and that was really in August 2015, and I'm not sure many people here can appreciate the significance of that. So TensorFlow was open source in November 2015, MXNet in January 2016, PyTorch appearing in 2017, so this contributed at least a little bit to forcing other companies into a similar open source strategy. So then we went through this entire Apache incubator process. It became in 2017 a top-level Apache project. And by the way, this is Beth Smith here. At the time of Spark Summit 2015, she was the general manager for software development at IBM. And she, in front of more than 1,000 people, announced that we're open sourcing SystemML and essentially established the Spark Technology Center. And I was actually sitting in this room here, somewhere down way in the back. All right, so in the last couple of years, when I became a professor at TU Graz, we reshaped essentially the focus on the end-to-end data science lifecycle, renamed it SystemDS, created a fork. We are later invited to merge it back into the main code line, and then it became essentially Apache SystemDS. Over the last 3 years, we also added new backends, and what we really learned through this decade of development is that the separation of concerns between what we want to compute, so the implementation of new algorithms, new primitives, separating this from the individual backends is of utmost importance and super valuable because the technology landscape will always evolve. So MapReduce was gone at one point and new backends come and go, but the investment into those algorithms and primitives is protected because they are shielded through this optimizing compiler. All right, now I talked about a hierarchically composed kind of infrastructure of built-in functions. So what we are doing now is to utilize our domain-specific language to implement a number of different algorithms. So here we see very simple linear regression via a conjugate gradient method, and here via a direct solve method that simply computes the normal equations and then solves those normal equations. On top of that, you essentially have just general mechanisms to dispatch between those different algorithms according to data characteristics. On top of that, you have primitives for feature selection. So here's an example of a stepwise linear model that essentially, given a data set, take the most predictive feature by building actual single feature regression models, and then in an outer loop go over all the remaining features, and in a greedy manner try what-if analysis and append those additional features and see what the accuracy is. And we keep appending in a greedy fashion those additional features until the ASC does not improve anymore. And the user, however, does not concern herself with all those different primitives, but can literally just invoke the individual primitives at a very high level. Now, SystemDS in general, so the separation of concern, so I hope you see that in those algorithms, so by the way, don't get distracted by this percent star percent, which is just a matrix multiply, because in R, percent is a way of defining new infix operators. The matrix package in R decided that percent star percent is the matrix multiply. We inherited that. But what is important to realize is that we are dealing with an abstract data type matrix. So you have X, this is a matrix. You're not hard coding, this is a sparse, dense, or compressed matrix, but this is all decided by the system infrastructure underneath. All right, now the first research project that makes another case for data independence is multi-level lineage tracing and reuse. So the first feature was really motivated out of data provenance, because at IBM we've seen quite a number of use cases where it would have been extremely valuable to take the exact same data set, take the lineage or provenance, and re-execute in order to compute the exact same model for comparison and debugging. Now, that is what we started with. So we now allow to actually running a machine learning program, tracing it, obtaining a lineage graph, so how were certain intermediates created, and then serializing this lineage graph into a log that can be shared for debugging with other people. But then on the other side, you can deserialize this log into this lineage graph again, and given the same inputs, completely reconstruct a program that yields the exact same intermediates. In order to make this happen for randomized operations, we keep all these system-generated seeds and make everything deterministic that we can actually recompute things. Now, because we keep all this information to reproduce intermediates, at the same time, we're utilizing it for reuse. So now the lineage, a hash over the lineage can be essentially a key in a reuse cache. So we're doing that for full intermediates. So imagine a simple grid search for a linear model where we iterate over regularization parameters and we call the model training for all those different parameters. Now on the surface, this looks like there is no reuse opportunity. However, opening up those individual primitives, the optimizing compiler sees that the regularization parameter is independent of those major matrix multipliers we're computing there. So those can be automatically at a very fine granularity being reused and just with that changing the asymptotic behavior. Even more so, I mentioned this stepwise linear regression feature selection. What you have to realize, doing those what-if analysis, where we append individual features, in the previous iteration, we already computed a large share of those intermediates, and now we're just appending a single feature. So we also support partial reuse, where we reuse the previous computed intermediates and only similar to the use of materialized views. So yesterday we had to talk about this, compute compensation plans in order to compute the full intermediate results. So that's number 2 for data independence. Case number 3 for data independence is compressed linear algebra. So in this particular piece of work, we are utilizing lightweight database compression techniques, applying them to numeric matrices, and performing linear algebra operations directly on the compressed representation in order to reduce memory bandwidth requirements, increase instruction parallelism, keep larger data sets in memory, and reduce the number of floating point operations. So the easiest way to visualize yourself that is via simple techniques like DDC, which stands for dense dictionary coding. There, we encode the distinct values in a dictionary and encode every value as the position in the dictionary. Classical database compression technique, where if the number of distinct values for a categorical feature, for example, is very small, so let's say we only have 256 different values, then you can losslessly compress that with a single byte per value, because you can fit 256 kind of different values into this 1 byte representation, reducing the memory consumption from 8 bytes FP64 to essentially a single byte. Even more so, we compute co-coding, where we create dictionaries of tuples, so reappearing values. And those reappearing values are then we're simply storing the distinct tuples. And that allows to reduce the number of floating point operations, because for a matrix vector multiply, we can perform, or matrix-matrix multiply, we can perform pre-aggregation on the dictionary according to its columns, getting a single scalar per distinct tuple. So if we co-coded 3 columns, you have 6 floating point operations, get this 1 scalar. And for every row, we are then just using a single floating point addition to add this to the output. Yeah. Now, in this particular work, so this was the ADBIS paper about in 2016. Now, Sebastian, my 3rd PhD student, actually continued this line of work. And now we are doing a workload-aware compression, where we utilize the information of our optimizing compiler of seeing what operations will actually be executed in the rest of the entire script, based on the premise, why should we optimize for compression ratio and hope that it helps performance? We are now actually taking the workload and optimizing for runtime. So if your data set comfortably fits in memory, we prefer operations that are much faster, reduce the number of floating point operations. If your data set is really large, then we optimize for compression ratios. And with that, it really automatically adapts to the cluster and workload characteristics. In the next couple of steps, and that will be the next paper for Sebastian, is really we're now trying to push essentially lots of this compression into feature transformations and early on into data cleaning pipelines already. Because if you think about it, in order to encode, so do dictionary coding and one-hot encoding from a data frame into a numeric matrix, you're computing already the dictionaries of distinct items, and then we throw them away and do compression later on matrices. So there's lots of potential to actually utilize the information we do in those feature transformations. The 4th case for data independence I want to make is this new backend for federated learning we've been building with a huge team of students, PhD students, undergraduate students, bachelor and master thesis, over the last 3 years. So the key premise of federated learning, which is a very popular topic, is how can we learn a central machine learning model without central data consolidation, based on privacy concerns, data ownership. So the classical thing is you have speech interactions on your phone for speech recognition. You certainly don't want to give this to a cloud provider to consolidate. You want to keep your data local. And how can we do that? The classical approach is to adopt a pyramidal server architecture where we initialize a model, and instead of consolidating the data, we send the model to your mobile phones. You run a forward and backward pass in a neural network to compute actual gradients, and then send us those gradients back, which are aggregates, not the raw data. And we essentially perform then additional steps. So we are supporting those classical federated pyramidal servers, but also federated linear algebra programs. So the general notation is that you can actually create a federated matrix saying this matrix is a virtual object, and its physical parts are on those different production sites. And then you run at the coordinator a program, an iterative training procedure. And whenever an operation hits this federated object, we are spawning federated requests. So we know exactly which parts of a matrix are on which server. And on those federated servers, we are simply then running partial operations and returning aggregates, and with that can execute general linear algebra programs. So we ran lots of benchmarks over an entire spectrum of traditional machine learning algorithms, so linear regression, support vector machines, logistic regression, clustering, dimensionality reduction, all the way to neural networks. And we compare our federated learning with the local baseline in a LAN setting, so local area network, so in our own rack in TU Graz, as well as in a wide area network. So Sebastian Baunsgaard, my 3rd PhD student, is actually during COVID, was going back to his parents' house in Denmark, and we utilized that for interesting experiments of actually running the coordinator, so you as a data scientist, in Copenhagen, Denmark, and the servers were running in Graz, Austria, so 1,300 kilometers apart from each other. And even in this wide area network, you see, so this is runtime in seconds here, that the overhead is quite moderate. In some cases, in a local area setting, and even in a wide area setting, so federated procedures even outperform local execution simply because if you have multiple federated servers, we have more resources to actually do compute. So if it's really compute intensive, like those convolutional neural networks, then it's much easier to amortize the overhead of data exchange. Now you might say, well, your baseline is just super weak, and with that, the overhead doesn't look that much. So of course, we also compare against scikit-learn and TensorFlow as kind of state-of-the-art systems, and it's kind of in the ballpark. So sometimes we are 2x faster, sometimes those systems are 2x faster, but it's really in the same ballpark, and hence you can really draw the conclusion that this moderate overhead is applicable and you will be realistic in other systems as well. All right, now the fifth case I want to make is fine-grained device placement. So we talked about modern hardware. So in the so-called DAPHNE EU project, we are trying to build an open and extensible system infrastructure, not just for data-centric ML pipelines, but for the combination of data management, query processing, machine learning, and high-performance computing, so numerical simulations. So this is a large consortium with 13 partners. Since end of last year, we have a 14th partner because we as TU Berlin. So I was the coordinator of this EU project, and we essentially now transfer part of it to TU Berlin and continue building the system infrastructure. Now in DAPHNE, we try to better support heterogeneous hardware, and we are going through an MLIR, so multi-level intermediate representation compiler stack. MLIR is, you can view it as a library of compiler infrastructure to make it more cost-effective to build domain-specific languages. However, some of the concepts from federated learning apply here too. Similar to placing a matrix onto multiple production sites, the same concepts apply to placing a matrix over multiple physical devices and then running, we call them vectorized execution pipelines, where we essentially take slices of a matrix and feed them through an entire pipeline of operations. So this is the pipeline of pre-processing, so C-scoring plus a closed form linear regression that essentially has just this XTX and XTY core matrix multipliers. You do them over slices and aggregate on the end to essentially effectively compute and simultaneously utilize CPUs, GPUs, and FPGAs. All right, so those were a couple of examples for the need for data independence and how we can actually accomplish that. In the very last part, and I can scale this as time allows me, I want to give essentially an idea of what we're doing next. So this was EOC grant I tried to write up over last holidays. Unfortunately, in June it was rejected. So now, right now, this is Schrödinger's proposal. So it's at the same time good and bad, but I strongly believe in it. But it's at the scale of about 3-4 PhD students for the next 5 years. All right, so we call this project Loreen, and the first motivation for that is there is a variety of redundancy exploiting techniques for data-centric ML pipelines, including resource allocation and elasticity, so not over-allocating in a cloud environment for a particular workload. Second, data sampling and composition. So some of you might have heard of core sets. How can we take a large data set and select the tuples that are in general much smaller, but training a model over it yields roughly the same accuracy than training it over the large data set. So there are a couple of learning procedures how we can select the highest quality tuples, and that is then of course useful because we can build many different models on top of them. Furthermore, there's a wide variety of work on sparsity exploitation, and I talked about lossless compression, but the mainstream research goes into lossy compression, so quantization, like min-max quantization. You take a numerical feature, take min and max, split it up into a bunch of bins, and essentially bring it into a U8 representation. There are also schemes for learned quantization, and furthermore, there's also work on weight pruning and connection sampling. So in order to make distributed training better, people essentially sample connections, learn those connections completely independently without any aggregations on different nodes, and then over multiple epochs essentially consolidate them. But the key takeaway from also super valuable research areas and something like sparsity exploitation, that's really, we're talking about hundreds to thousands of papers, they're all applied in isolation. So you as a data scientist struggle with, okay, great, I have all those techniques, I have a new data set, what do I apply? How do I actually jointly apply those different techniques? And that's exactly what currently is still a trial and error process. And we want to systematically, jointly apply those different techniques. So how we want to do that? Lauren, holistic redundancy exploitation. So just to give you a rough idea how sparsity exploitation is, for example, done. So normally you try, so W are your weights, so this is your model. Imagine just a single weight matrix, single layer network, for example. You have some error that you see given the weights on your data set. Usually, in order to avoid overfitting, you also have a regularization term where if the weights are really large, this penalizes essentially those large weights in the loss function. One way of now incorporating sparsity is to include, similar to lasso regression, the absolute values of your weights into the loss function. What that leads to is if a weight does not significantly reduce the loss, it's better to pull this weight down to zero, creating essentially sparsity in the weights. And we can learn that iteratively and ultimately get a sparse weights matrix, allowing us to reduce floating point operations during scoring once we actually employ this model. Now, if you think about that, the option to completely pull the weight to zero or not is very coarse-grained. So what we want to do is, in order to simultaneously incorporate lossy compression, is to include the number of distinct items per feature or per weight slice into the loss function as well, which instead of pulling a weight completely to zero, we say, instead of FP64, we quantize this particular weight to 8-bit or to 4-bit or to 3-bit and learn this automatically. So the core idea is to take all the lossy decisions, pull them to algorithm level and learn them actually, and then build system infrastructure to perform lossless sparsity exploitation under the covers automatically for a user. So we don't have to make any assumptions. It's at algorithm level, user can still tweak it, set the right parameters, and we only perform lossless really kind of optimization under the covers. There are a couple of ongoing projects. So just last week kicked off the first couple of master theses in this context. And this is of course a humongous space, and we are now looking at subspaces and trying to solve them correctly first and then extend them furthermore. So the first subproblem I want to pitch is the sampling. So sampling usually has an optimization objective, something like minimize the sample size that comes out, subject to not degrading accuracy too much. Okay. On the other hand, the very valuable data augmentation says, well, I have an original data set, maximize accuracy subject to do not make the data set too large. So as I mentioned earlier, data augmentation is a very valuable technique, widely applicable. But right now you choose, go down and preserve the accuracy, or do I improve the accuracy? We believe there's a simple hybrid in between that's actually outperforming both of those extremes. So instead of just sampling or just adding tuples, why not add a few tuples that are currently underrepresented in our data set and otherwise sample out things that are just redundant that we already have in our data set. So we don't have the total solution yet, but I just pitched the problem here that ultimately we want to create a data set that has a few blue and red tuples in between, potentially improving accuracy while even making the data set smaller. And the sampling is super compelling because it has the potential to, by orders of magnitude, actually reduce the training effort. All right. And last slide is then that overall, we have those outer loops for data-centric ML pipelines. And we simultaneously want to apply sampling, sparsification, compression in a holistic manner, leading to we might perform connection sampling while some of the connections are still compressed in certain representations. And then this leads essentially to a multi-objective optimization with hierarchical multiplexing, where somewhere in the hierarchy you are then enforcing a particular sample and trying to still incorporate it into a larger training procedure. And if you're now saying, well, but ultimately only accuracy matters. What we are doing here in those data-centric ML pipelines, a lot of those outer loops are actually selection steps. Select me the best smart, or select me the best cleaning pipeline, select me the best configuration for data augmentation. So one interesting question is, are there proxy models, those really kind of redundancy exploiting strategies that are good enough to select exactly the same pipelines that we would have selected with a full model, and then just once at the very end, train the full model instead of training it tens of thousands of times. All right, so that's all I had. Quickly wrapping up, first, data-centric ML pipelines are very important because we want to create data sets that have good coverage and improve our end-to-end applications. They are increasingly complex and hierarchically composed out of ML primitives. And they obtain, the more complex those pipelines are, redundancy in terms of data and operations are inevitable, which motivates essentially system infrastructure for optimizing compilers and runtime infrastructure. And in Loreen, we are trying to learn the lossy aspects of it and automatically provide system infrastructure for the lossless aspects. So in general, since last year, I took over the chair at TU Berlin for Big Data Engineering, and we are doing system-oriented research. So we're actually building those large two open source projects, Apache SystemDS and DAPHNE, with multiple different major topic directions, where many of them actually go into a form of specialization for workload, for data characteristics, for the domain. So I strongly believe we also need to better look into applications. So specializing not just for data cleaning or data preparation, but specializing for healthcare data, specializing for recycling, and multiple different domains that have very specific characteristics that gives us opportunities for improvement. And fundamentally, I believe that building all that, the more we specialize, that can totally hurt an user. So it is about the right abstractions that are useful for users and interdisciplinary collaborations to actually understand those domains that we want to optimize. So this is always really a back and forth, and usually interesting things come out of those collaborations, even though it's a little bit additional work. But I encourage everybody to be open-minded in that regard. With that, thank you so much, and I'm happy to answer questions.
Thank you, Matthias. So we have a fair amount of time for questions. So any questions, please?
Thank you very much for the inspiring talk. I have a question regarding, well, it's two related questions, you'll see how. First of all is elasticity. So when you choose compiling things, you lose elasticity. And my question is whether we can imagine that having all these different hardware and thus these decisions, whether we can still dream of elasticity at runtime. So that's the first thing. And the second thing, which is related, is that normally the execution of a data science pipeline is not linear. So you go back and forth, and then you test, etc. And testing means also that you have to make decisions on the hardware. So to which extent is it possible to leave it all to the system decision, and to which extent it is a programmer that still has to give hints in order to deal with all these decision making?
Yeah. Awesome questions. They are so large that I could actually talk half an hour about it. But go back a little bit to resource allocation. So our first work in resource allocation was actually a Sigma 2015 paper. It was back when I was at IBM. We had our summer interns, second, third year PhD students, and we had a great student from Duke University, Boehm Wang. He's now at Microsoft. And there we essentially tried to give him an input data set in a program you want to execute. Select the right cloud resources to allocate for. And we did that, but there are some programs where you have data-dependent intermediate sizes and other characteristics where you simply don't know upfront. So we then integrated this entire mechanism for resource elasticity into our dynamic recompilation. So at certain points in the program where intermediates are unknown and we have to fall back to really inefficient fallback plans that work for all data characteristics, there we mark those plans, and then the compilers actually trigger during runtime, recompiling either a function or individual subprograms. And in this particular resource elasticity work, we then did a migration of, at this point, computing what are the actual best resources we should, allocating a new one, migrating our stuff over there, releasing that. So this is quite some effort, but possible, and in general, very valuable. And for us, this was a very practical means of actually making it happen, versus prior work had a lot of assumptions. So prior work, often you will see a lot of those works that say minimize costs subject to a time constraint, or minimize execution time subject to a time constraint. We didn't do that because for most machine learning algorithms, they are convergent-based iterative procedures. So without knowing the number of iterations, you can't give a constraint on the time anyway. So we said optimize for performance without unnecessary over-allocation, so memory or CPU resources that you could anyway not utilize, and kind of with that restrict your resources. The second aspect, human in the loop. So there is a beautiful paper from Phil Bernstein and Sergey Melnik in 2007, where they reflect on schema matching a decade before. And they said a beautiful sentence of saying, despite all this work from a decade of our entire community, why is it still so labor intensive to develop schema mappings? And they came to the conclusion it's because the specification of meaning in the schema alone is very weak, versus the mapping a transformation program needs to be precisely engineered to actually work. And with that, because of this ambiguity, it is almost hopeless to do full automation. And we recognize that. And what we often try to do is to make infrastructure extensible. So for example, in our data cleaning pipeline, we allow a user to plug in new cleaning primitives, so they're hyperprimitives, and we then include this into this mechanic kind of validation and systematic evaluation of things. And we often give, for model debugging, so slice line, we give the top K out, which is still a user interaction, so give good candidates. So can we build tools that make it easier, instead of going through every possible combination, narrow it down to a few candidates that then a user can actually interact and evaluate. And we talked in the DI panel again. So for fairness, the same thing. Fairness is not a technical problem, but a socio-technical problem. So we want to build tools that simplify thinking about and seeing problems in the data sets and models we're doing. Yeah. Awesome. Excellent question.
Thank you very much for the very nice and inspiring talk. I really appreciate your last very bullet points when it comes to interactivity to collect abstractions and having the progression. So this might be a follow-up to the first question. What are, in your experience, the best practices to collect efficiently and effectively these abstractions?
I didn't get the last two words.
What are, in your experience, the best practices in how to collect effectively and efficiently these abstractions?
Oh, okay. Okay. That's an excellent question, and upfront, I don't have a super good answer for that. I can tell you about my learning process, right? So we started with SystemML focusing on handcrafting custom machine learning algorithms. So we were at the level of individual machine learning algorithms, how you design new algorithms and efficiently build them via matrix multiplies and other primitives. And it took me way too long to realize. So we were in an environment where we had a diverse team of people from machine learning, from data science, more applications, from essentially data management, distributed systems. But it was a very biased environment where everybody had a PhD, everybody knew how to craft certain things, and that is just not the reality. So out there, in terms of data scientists, 1 out of 1,000 would actually craft a completely new machine learning algorithm. Most people would call certain primitives, so existing algorithms, chain them together with the experience of their. So what we then ended in Graz, when I was senior enough to actually realize all those things, that we build higher level primitives, but on top of our own domain specific language, that we get the benefit of still being able to collapse it through the compiler, but giving actual primitives for automated data cleaning or model debugging. I think, and this is right now Wild West, so we're in this explosion, everybody's proposing things, and as always, there will be kind of a convergence where certain primitives will turn out to be very effective, and they will remain and establish themselves. But proposing those higher level, not just in terms of algorithms, but debugging primitives or pre-processing primitives that out of the box are general enough to capture a subset of problems, they're super useful, and this is an unbounded space. So there's lots of work to be done, actually. Yeah. Thank you.
Okay, you are doing very advanced, extremely difficult research. Full respect.
All my students. Just.
I would like to go back to the beginning of your work. You were mentioning about data cleaning, and I just finished a project, financial sector. That was about data cleaning customers' records, over 20 million rows. And from my experience, it is impossible to perfectly clean all data. Okay, if you have 1,000 records, it is possible. And what you said was that user involvement is necessary. I fully agree with this. And but this cleaning process will, for large data sets, will not produce 100% clean data. What is your opinion on, or what is your experience in this problem?
Excellent question, and this, again, a mixed experience. So in Graz, I was giving the large data management in the bachelor, mandatory lecture, and in those mandatory lectures, you have 2 distributions, 15-20% distribution of students that actually want to hear everything and take away a lot of things, and there is a large portion of students that just want to get through it, do the minimal effort just to get through it. Our course was very challenging because we had practical exercises where we actually gave them real-world data, and every semester a new data set. So I just picked one, and all of them were dirty. I actually had the hope that as we build this data cleaning infrastructure, that we automate our process of preparing the exercises for this course as well. And to be honest, we did not come to the point to actually do that because it's just so diverse in terms of things, and many things have to come together. I would say here, this data cleaning pipeline is good for certain types of errors. So we are supporting swaps of attributes where entered in the wrong fields in a web form, typos, outliers, missing values. But in reality, often, so for example, one semester we took the DBLP publication dataset, and this is a curated dataset. So this is probably on the better end of datasets. And I wrote an XML extractor to actually get just the data management venues, consolidate them. They're all inconsistent still. And I make a lot of mistakes under time pressure, leading to a lot of errors in the dataset. And then we went through a lot of iterations to actually get it reasonably good. Because of those custom extractors and additional primitives, there are many different sources, structural outliers and kind of structural in JSON things, subtrees hanging in the wrong application. And there are dedicated strategies how to handle that. And composing all of that right now is a semi-manual process. We hope that we can, by integrating more of those strategies, make it more streamlined, but it's really building multiple tools, seeing what works, and then trying to integrate them together. And I completely agree. There are fields which are just intrinsically hard, and even we as humans, so I, in some domains, simply can't say if this is correct or not. And that, of course, makes it very hard to verify things. We have the only advantage that we have here in comparison to normal data cleaning, like Baran and other frameworks that worked on data cleaning for a long time, is that we have the application as a signal that we can use to enumerate and at least parameterize those primitives that we have sufficiently good. And then you can compare the accuracy on train and test set was this, and in some cases we actually improved accuracy by 10%. And so is it perfect? Probably not, but it definitely led to an improvement. That's what you can observe. And more work is needed for, and there are works for JSON, for example, where you simply count. You build count trees, how often which attribute appears in which structure, and then you can make assumption and saying probably those 2 instances here should belong to the 20,000 that were in a completely different structure. Yeah. But great point, yeah.
Thank you.
I'd like to ask you, how do you relate this what you've done a lot in this field to software product lines? This recalls very much software product lines. You recognize this already, and moreover, separation of concerns, like cross-cutting concerns, aspect-oriented software development, because it is also related to software product lines, where when you using this approach, you can separate the features more easily and reapply transformations and so on. So how would you comment on this?
I'm not the entire expert in that, but at least what I remember from software product lines and feature-oriented systems is that you literally, as a form of variability, you devise multiple components that satisfy the same functionality that you can quickly swap out. And there has been some work in the data management community to build a composable data management system of essentially having different index structures and different things. And you can create a concrete instance as a selection for those different things, which I always viewed as a rather static upfront configuration, which is great for composability and reuse. Versus what we're doing here is a little bit more fine-grained. If I go to those different backends, we are actually compiling hybrid runtime plans. We are in a single large, it's conditional control flow, and per basic block, you have then large data flow graphs. And for any node in this data flow graph, we might execute a node in distributed operations and other in local operations. And according to the size of intermediates, as I mentioned earlier, we are recompiling during runtime where this entire mapping, now we know the data sets will fit in memory, so we compile a local operation instead of a distributed operation. It's really, really low latency during runtime, actually. But there are absolutely relationships to each other. Yeah? And I actually, during my postdoc and later research stuff, member time at IBM, learned a lot from compiler technology and software development. And initially, when it was an IBM product, we were actually closely, as researchers, interacting with the development team and utilizing rational kind of software development stacks and stuff like that at IBM. Yeah. I'm not sure if that answered the question, though. Thank you very much.
We have time for one more question. Let me ask one then. Do you think that in the future we will see something similar to the concept of database for these very complex workflows? Will we be able to reach there at some point? I know that we are still working in optimizing pieces and just playing here and there in the workflow. Do you think that this is possible? Will we be able to reach that far?
It's an excellent question. I hope so. I don't think that right now this will happen soon because of the dilemma between standards and innovation. So there are a couple of standards like ONNX and other exchange standards for the description of neural networks and kind of operator graphs. When I was at IBM, actually team members from IBM tried to merge this into TensorFlow, and it was rejected by TensorFlow. So the ONNX support for TensorFlow, because it would limit what kinds of new operations they could add. So right now we're still in this exploding phase before there will be a consolidation phase and people settle on a standard. And by default, the individual companies, they have no interest to settle on a standard, but they are forced because all the other companies are forced in a standard. So this is larger kind of decentralized processes that I hope will happen. But once we have a standard and people agree on a specification language, on a domain-specific language, then it's much easier to actually focus on system internals. Right now, it's always, you have to pitch your custom language that nobody wants to learn. So it's much harder entry for new systems coming in. And we are still very niche. I want to be very clear about that. Although we have an R-like syntax, and R was way more popular than Python back in the 2010s when it started. Right now, there are other new frameworks like Mojo that essentially try to be a superset of Python and automatically compile the entire stack. So I believe, yes, in the future, yes. Right now, there's still this explosion of new specification languages and APIs.
Well, thank you very much, Matthias, for this very inspiring talk. So the coffee break is ready, so please let's thank one more time.